You may have heard that there is a fundamental rule in physics. In a flat spacetime vacuum, an object with mass can approach the speed of light indefinitely, but it can never actually reach it. On the other hand, massless objects can only travel at the speed of light. However, there's a loophole. The key condition for this rule is that spacetime must be flat. If you can bend it, you open up the possibility of exceeding the speed of light. So what does it mean to bend spacetime? Imagine creating a flat sheet representing spacetime. Ignoring friction, any object moving on this sheet will maintain a constant speed in a straight line. Now, if we introduce a massive object, like the Sun, its significant mass will warp spacetime. What if we add another sun? The combined curvature they create will draw them together, eventually causing them to collide. Sprinkle in some planets, and they'll move in orbits. The most fascinating case is our moon orbiting Earth, which in turn orbits the Sun, but I assume you're already familiar with that. Massive and dense objects can compress spacetime, causing it to curve. If the object is extremely dense, like a black hole, not even light can escape, suggesting that objects falling into black holes can exceed the speed of light. Another example of spacetime stretching occurred in 1929 when astronomer Edwin Hubble found that galaxies farther from us are moving away faster, with no upper limit on their speed. In fact, calculations show that galaxies more than 14 billion light-years away are receding faster than light, a phenomenon known as cosmic expansion. Can ships really move by squeezing or stretching spacetime? The answer is yes. You may have seen this experiment. A drop of soap in water reduces the water's surface tension, causing the molecules to spread out. We can liken this to the stretching of spacetime. If we apply soap to the rear of a spaceship, the moment it is released into the water, spacetime at the rear stretches, while the front contracts, propelling the ship forward. Both warp drives and artificial wormholes, in essence, utilize the bending of spacetime, enabling speeds hundreds or thousands of times faster than light. However, the design for faster-than-light ships remains theoretical, mainly because we can't create massive and dense matter out of nothing, and we haven't even found traces of negative energy or negative density matter. So, according to scientists, we'll have to wait at least a few centuries for warp travel. So, let's get back to reality. Given the technologies we can currently see, can we venture out into space? Whether it's chemical fuel, ion drives, controlled nuclear fusion, or antimatter propulsion, their core principle is Newton's second law. To move faster, you need a greater force, right? However, it's not that simple. For instance, with today's chemical rockets, to get more thrust, you need more fuel. More fuel makes the rocket heavier, reducing acceleration. Scientists have thus introduced the concept of specific impulse, which is the amount of momentum a unit mass of propellant can produce. Ultimately, the amount of fuel isn't as meaningful as the engine's efficiency. Let's begin by drawing an analogy with chemical fuels. There are many types of chemical fuels, some solid and some liquid, but fundamentally they all rely on chemical reactions. Take liquid hydrogen and liquid oxygen for example. When ignited, they undergo a reaction that releases energy by rearranging chemical bonds. This produces high-pressure, high-temperature water molecules that are ejected at high speeds. In this process, the energy stored in chemical bonds is converted into kinetic energy. However, the efficiency of converting this energy in chemical fuels is relatively low, around 35%, with much of it being lost as heat. After decades of development, the efficiency of chemical rockets has pretty much reached its theoretical limit. Solely relying on chemical propulsion, it's highly unlikely we'll venture out of the solar system. So, what allowed the Voyager 1 and Voyager 2 probes to escape the solar system? They used gravitational slingshots. I found this concept amazing before I understood it. In essence, when Voyager 1 approached a massive celestial body like Jupiter, its speed increased as it came closer and decreased as it moved away. This is an example of energy conservation. While this may resemble an elastic collision, the crucial point is that Jupiter is also in motion. It orbits the Sun at about 13 kilometers per second. So, while Voyager 1's speed relative to Jupiter remains unchanged, its speed relative to the Sun does increase. A common misconception is that the larger the celestial body, the more effective the slingshot. This isn't true. Even though the Sun contains 99.8% of the solar system's mass, using it for a slingshot won't help you escape the solar system. Gravitational slingshots do have limitations. They require precise timing. For example, the Parker Solar Probe used Venus for 7 slingshots over 6 years. Moreover, the next opportunity to perform multiple slingshots like Voyager did won't occur for another 175 years. But one indisputable advantage of gravitational slingshots is that they don't depend on the mass of your spacecraft. Whether it's a battleship or a marble, the acceleration would be the same, given the same initial speed and entry angle. Unfortunately, the speed gained from gravitational slingshots is disappointingly low. Even if we wait another 175 years and use Saturn, Jupiter, Uranus, and Neptune for perfect slingshots, we'll still not exceed an interstellar speed of 40 kilometers per second. So, do we have other options? Yes, ion propulsion. This isn't science fiction, it's a real engine. NASA developed the first ion thruster back in 1959. The principle is straightforward. You need a high-voltage inverter capable of generating up to 40,000 volts. While this sounds dangerous, the electric shocks you get from taking off a sweater in dry winter air can be as high as 20,000 volts. With low currents, it's still quite safe. Everyone knows that electric charges like to gather at sharp points. By connecting the positive terminal of an inverter to a nail, we can concentrate positive charges. Next, prepare a cut-open soda can connected to the negative terminal. Voila! You've just made a basic ion thruster. When powered on, electrons will flow from the nail to the soda can. This accumulates a lot of positive charges at the nail and negative charges at the soda can, creating a cone-shaped electric field between them. Air molecules near the nail lose their electrons, becoming positively charged ions. These ions are then accelerated by the electric field towards the can, generating what is called ion wind. Of course, in this experiment, we're using air as the propellant. However, there's no air in outer space, so fuel is still required. Modern ion thrusters commonly use xenon as fuel. They bombard xenon atoms with high-energy electrons, knocking electrons out and turning the atoms into xenon ions. These electrons are absorbed by the positively charged walls, and the xenon ions are then accelerated out by the powerful electric field at the thruster's rear. Ion thrusters are astonishingly efficient in terms of fuel ejection speed. To draw a comparison with chemical rockets, the latter typically expel water molecules at speeds of about 4 kilometers per second, whereas ion thrusters can achieve speeds up to 40 kilometers per second, a tenfold difference. According to NASA, chemical rockets have an efficiency of around 35%, while ion thrusters boast an impressive 90% efficiency rate in converting electrical energy. The first spacecraft to use ion propulsion, the Dawn mission, launched in September 2007. You may be surprised to learn that its xenon ion thruster had a thrust of just 92 millinewtons, comparable to the force of blowing on a piece of paper. Why so small? Although ion thrusters are highly efficient, they're often solar-powered. With many other instruments also needing solar power, it's hard to achieve the millions of newtons of thrust that chemical fuels offer. But don't underestimate that 92 millinewtons. With continuous acceleration, it can bring Dawn from 0 to 100 kilometers per hour in just 4 days. NASA's most recently tested X-3 ion engine broke numerous records, with a thrust up to 5.4 newtons, an over 50-fold increase compared to the Dawn mission. Scientists estimate that with constant acceleration, a spacecraft equipped with a nuclear-powered ion thruster could eventually reach speeds up to 220 km per second. If we were to combine all of today's cutting-edge technologies and launch another Voyager mission, incorporating chemical rockets, gravitational slingshots, and continuous ion propulsion, we might even reach speeds up to 300 km per second. This far exceeds the Voyager 1, showing that human technology is indeed advancing. But what if we want to take a trip around the closest star, Proxima Centauri? The journey would take over 4,000 years. Is there no hope? Well, don't lose heart. Within the next 20 years, humanity is poised to make another monumental leap forward: controlled nuclear fusion. The news about fusion has been buzzing lately, and scientists are confident that this technology will become a reality within the next 10 to 20 years. If that happens, the only event in history that could compare would be the Industrial Revolution at the turn of the 19th century. So why is nuclear fusion such a game changer? We've talked about the efficiency of chemical fuel being 35% and ion thrusters being 90%. These efficiencies are a measure of how well these technologies convert their original chemical or electrical energy into kinetic energy. But when measured from the perspective of nuclear fusion, these technologies are trivial. Fusion generates energy so efficiently that almost less than 1% of mass gets converted directly into energy. According to the mass-energy equivalence equation, just a few grams of hydrogen, after undergoing fusion, can produce as much energy as hundreds of tons of coal. How efficient will fusion propulsion be in converting energy into kinetic energy? Well, that's yet to be determined. But in an ideal scenario, if all the energy generated by the fusion of two hydrogen nuclei were loaded onto a helium nucleus, it could be propelled at 0.1 times the speed of light, or about 30,000 kilometers per second. Remember the ejection speeds we talked about for chemical rockets and ion thrusters? 4 kilometers per second and 40 kilometers per second, respectively. With fusion propulsion, the peak speeds of interstellar spaceships could be around 10 to 15% the speed of light. With that kind of speed, humanity could achieve three main objectives: colonize the solar system, engage in interstellar mining, and explore Proxima Centauri. If you wish to go even further, then antimatter propulsion comes into play. The concept dates back to 1928, when Paul Dirac formulated the famous Dirac equation, predicting the existence of the positron, which was confirmed in 1932. Antimatter became fully conceptualized when antiprotons and antineutrons were discovered in the 1950s. Antimatter is interesting because when it comes into contact with matter, they annihilate each other, converting all of their mass into energy. Fusion is impressive because it can convert mass into energy at an efficiency of less than 1%. Antimatter annihilation is 100% efficient. Just a few grams of antimatter fuel could equate to over 400 tons of rocket propellant. If you had a kilogram of antimatter, you'd possess the energy equivalent of 3,000 Hiroshima atomic bombs. Creating a functional antimatter engine would hinge solely on how much mass we have at our disposal. However, the production and collection of antimatter are currently formidable challenges. Any contact with matter results in immediate annihilation, making its storage exceedingly difficult.